So good afternoon, everyone. Welcome to this, sorry, what month is today? It's October.
It's 12.
To the October edition of the mini school. I'm very happy I don't have to introduce her to you again because you met her already last week, Laure Gouba, who is now based at ICTP in Trieste, and today she will continue her mini course on green functions for differential equations. Yeah. So Laura, please, we are very happy that you are back with us. You are welcome to share the screen and to start your presentation. And while you do so, the usual reminder to the participants to use the Q&A to ask questions. And since we are not so many, at the end of the talk, you can raise your hand and ask questions in person. I will give you the rights to talk. Yeah. So Laura, please, you're welcome to start.
Thank you very much, and welcome to all those that are present. And I would say it's a good morning for who just start with day, and a good afternoon, everyone. So welcome to the second session on green function for ordinary differential equations. And as this is the title for the mini course of this month. And as I already said last week, the goal is to investigate the solution of non-homogeneous second order differential equation using green functions. So with that, let me stop with this. Last week, we already started where I gave some generalization about second order differential equations. I am looking for my file of last week. Let me see. New share, let's see. I get confused with my different file. And share. Okay, I don't know. I get confused with various file I have, and new share. Yes. Bon, I stop.
Is there anything that we can help, Laura?
Yes, I have various files that I should have seen, but when I share, I don't see how I get out of my full screen mode.
Just press escape.
Escape, yes. Oh, that's true. Okay, I get it now. Okay, thank you. So last week, I gave the organization of the mini courses as follows. That the first session that was last week was about generalities about second order ordinary differential equations. And today I will talk about integral operators and differential operators. So for the program of today, I gave you the program of today. I want to follow a new share. Stop here. Mm. Yeah. Okay, finally I am on the board. I'm sorry for all those attention. So for today, today is 12 October. So today is the session 2 of the school. Session. And today will be about integral and differential operators. So for today, I will start giving some notations that will be useful for the understanding of the rest. Then in the notation, I'll start with the direct delta function Then I want to introduce abstract vector f and its component f of x, where x is a continuous variable on the interval AB. Then in a second point, I will talk about integral operators. Then in a third point, I'll say about formal differential operators. So this is what I hope to cover today, and I think I should cover it. And if you do remember last week, introducing generalities about second order non-homogeneous differential operators, I was expected to give you a few lines about the method of variation of constant. But I will do that next week. I will take a few minutes to just tell you about this method and why an alternative to this method is the method by the grain functions. Okay, so but today I will talk about integral and differential operators, and the session of today and last week's session are considered as preliminaries in order to have a good understanding of what I will see next week in the third session. So let's start with the direct delta function. So notation, first point of the day. So first point of the first point is the direct delta function. Okay. The direct delta function is a useful mathematical object that has various physical background in many different disciplines. Okay. And there are many ways to actually define the direct delta functions. There are many ways to actually define the direct delta function we choose, for instance, the following. Okay, let's introduce the following definition. Okay, we can introduce or we can give this definition that, of course, fit probably what we want to do. If a function f of x satisfies the two conditions that are condition 1, f of x is equal to plus infinity for x equal a certain point x0, 0 otherwise means when x is different from x0, and second condition C2, f of x is the integral minus infinity plus infinity f of x dx is equal to 1. So if a function f of x satisfies these two conditions for a certain value x0, then f of x is called the direct delta function and usually denoted denoted f of x is delta x minus x naught. So this is among various kind of definition of a delta function, what we can have as a definition. And I will not be discussing too much about that because it's not the main issue here, but I just give a definition. If you want more to know about delta function, you can check, for example, in the reference book or in the literature. Okay. So it's called delta direct function, but most of the time you can just hear direct functions for simplicity. So let me stress that also. It is usually called direct function for simplicity. Okay. So these are the main properties of the direct delta function that we need to be aware of. So these properties that probably for what I will be saying next, we'll be using highly and also next week. Then we have delta x minus x0 is equal to 0 if x different than x0. We have integral minus infinity to plus infinity of delta x minus x0 is dx, sorry, is equal to 1. We have integral minus infinity to plus infinity delta x minus x0 f of x dx is equal to f of x0. And this is usually called the property of the delta distribution. It's one of the useful property that I will be using very soon. And we have the integral of AB delta x minus x0 dx is equal to 1 if x0 is between A and B, okay, belong to the interval, and 0 otherwise. Okay, so this is what I want to briefly say about delta, direct delta function, and that will be using some of the property very soon. Okay, so let's continue. Now I would like to introduce in a second point of notation abstract vector f. I hope you are all familiar to the direct notation for vectors and its component f of x. Okay, this I want to say is about how we consider this kind of abstract vectors. So let's consider the entire set of values of a function f of x as representing a vector f in other words, the number f of x, of course, where x is a continuous variable, are treated as the components with index x of an abstract vector f. Okay. So when we have a function f of x, and when we consider all the entire set of value of these functions with x as a continuous variable, then these may be seen as representing an abstract vector that I call f with these notations. So the vector f belongs to an abstract function space f, which is defined as the linear vector space whose vectors are represented by functions defined on an interval AB. So what did I say? What I said is that we have a function space f, and we have those vectors that belong to f, and those vectors have as a component, how do I write this component? As component f of x, where we have x belong to the interval AB. This is what I just want to introduce. Now we assume, since we want to, we are talking about function space, we are talking about vectors of the function space, we are talking about components of this vector. So it's also good to say about a basis vector, because a component is also has to see with basis vector. So we assume, since, let me go to next page. Oh, okay, it's fine. Since the component of the vectors are defined with respect to some basis we formally introduce such a basis. In other words, what would be the basis that we will consider here for these vectors? So such basis consists of vectors x where the index x that labels these vectors is continuous. Then it means I have this. Then since the index are continuous, I mean the x are continuous, it will be difficult to set certain things like normalization condition, but we can still say about orthogonal conditions. So we assume that these vectors, if I have two vectors, the basis vectors are orthogonal in the sense that if I have x and I have x prime, then they are orthogonal. Orthogonal means that the inner product is equal to 0. But now, with respect to the normalization conditions, we cannot set it yet. So we cannot have the normalization condition. Since the variable x is continuous, since x is continuous. Okay, this is the point, but we will see how we define that. Now, as a setting, we set by definition f of x is equal, I put here by definition, x inner product xf. You know that we have our abstract vector f that has a component f of x, and with respect to the basis x of vectors x. So by definition, we said that f of x is equal xf inner products. And with respect to this basis, with respect to the basis x we can write f as the abstract vector f can be written in terms of the basis element and its component as follows: integral a b dx wx f of x x, where wx is called the weight function. And here, if you want, you can, if you are careful, you can do the analogy, because if you, what we know, if you have a vector and you have a component of the vectors, I mean, when we do that in discrete case, and you have also the basis, then you can still write the vector on term of as a linear combination using the component and the basis vectors. And you can see that this notation, integral a b dx wx, is similar to when you have a summation sum r in a discrete case. But I just want to say that this notation is nothing than generalization of what you have in a discrete case. So now that we set for a function space where element has abstract vector f, and we have an idea of what we want to take for this function as basis, and we know how to write, to use the basis to have an expression of the component f with respect to the vectors. And we know also how to write each vector in this function space as in terms of a basis element and the component. Now let's check what is the expression with respect to that. What would be the expression of the inner product of two basis elements, since we cannot set normalization condition? So now let's check. Let's check the expression x prime x, inner product of two vector basis, and y we cannot have the normalization condition x prime x inner product is equal to 1. Okay. So let's check that. So in order to have an expression of this inner product in a good way, let's start with again with f is equal to integral ab dx, the weight function f of x and x. Okay. Let's multiply from the left by the vector bra x prime. So what do I have? I will have x prime f is equal to integral ab dx omega x fx x prime x. Okay. But from what we set as definition here, from what we set here, we can then say that this is f of x prime, and this would be equal to the integral ab dx omega x f of x x prime x. And if we do remember the fact that we have this expression, where did I show that? If we do remember that expression or that property of the delta direct function, then we can say that this expression implies that omega x x prime x has the property of the delta distribution and we cannot have x prime x is equal to 1. With respect to that, we cannot set that we have a normalization condition, but this expression, the fact that at the left hand side we have f of x prime that is equal to the expression that we have at the right hand side, we can say that x prime, the inner product for two vector bases, is equal to 1. We can set that square root omega x prime delta x minus x prime. That if we treat delta x minus x prime as a formal generalization of the conical delta function, then we can see this as 1 over omega x delta x minus x prime, and the same thing is 1 omega x prime delta x minus x prime. So here what we consider is that here we treat delta x minus x prime as a formal generalization of the conical delta. And the conical delta is when you have delta ij is equal to 0 if I equal j, and no 1, sorry, but 0 if I different from j, and 1 if I is equal to j. This is delta conical function. Okay, with that, I think I have what information we need for this abstract vectors and its component. we almost cover it, except that I will just add what is the scalar product for two vector function on the function space, and what would be the identity operators. So scalar function, scalar product, sorry. Scalar product, this I just give it. For the scalar product, we assume that the scalar product is given by fj of 2 is equal integral ab, the weight function, conjugate f of x, g of x, dx. This for the scalar. Okay. And then, of course, w by x is the weight function. Then identity operator. Then you can also, in the function space, the identity operator can be written in the form E is equal integral AB dx vector x omega x conjugate to vector x, that is the ket Weber. Okay, this can be seen as the identity operator, and also how one can consider the scalar product. And here, in fact, weight function is very useful when one defined scalar product. And also, if this was not a mini course, we'll see also that the weight function can be chosen such that if you have a second order differential operator with respect to wave function, there are conditions that this differential operators will be self-adjoint or Hermitian. So I don't mention into that. Let's continue now. Next, I want to talk now about integral operators. Integral operators. So second point now, integral operators. Okay. So we call an operator an integral operator if using the notations, that's why it's useful to give first the notation, we have just introduced it can be written okay. Oh, thank you, Professor Glethiel. I'm glad you were following. Okay, thanks. Okay, let's see. If it can be written formally as a double integral, that is k is equal to integral ab, since it's double, I double, variable x second dx prime, vector x second, weight function with respect to variable x second, a function k that depends on two variables, x second, x prime, another weight function that depends on the variable x prime, is still the same weight function, but depending two variables, and x prime. So this is how, with respect to the notation I already given, I can formally write an integral operators as a double integral. So this is how we define. Now that we define that, let's see what is the action of this integral operators on the vector f. Okay, so now I consider a vector f in the function space f. Then I say g is vector g is the action of this integral operators on f. Okay, and that is equal to, let's say, I just rewrite that, integral ab dx second dx prime x second omega x second k x second x prime omega x prime. Now x prime in a product f. Okay, so what will happen now? For the moment, we know that this expression is f of x prime. Okay, now if I want to have the expression of g of x associated to my vector f, my vector g, what will happen if I say is x j, this is nothing than g of x, and this is equal to, if I apply bra vector x to the left hand side, then I will have integral ab dx second dx prime, then comes x second omega x second k x second x prime omega x prime f of x prime. Okay, but we have already defined, just in my previous slide, what we mean by the inner product x second. This is delta x minus x second. And since I have omega x second, it makes sense to do the ratios of omega x second. Okay. So now you can see I have already substituted this expression by fx prime. I have this expression that is equal to this, and I have this that is equal to g of x. So let's continue. So we'll have then g of x is equal to the integral a b. Let's pull all variables depending on x prime to one side of the integral, and we remain with one other side of the integral depending on the second variable x second. Then I will have dx prime omega x prime f of x prime integral a b dx second delta x minus x second divided by omega x second. This replaces the inner product x second, omega x second, k x second x prime. Then I just have to rearrange this expression, and if I rearrange it, I have then g of x is equal to integral a b dx prime omega x prime f x prime. Let me write it well here. X prime integral a b. Then you can see that those expression can go away. I can cancel that. Then it will remain then dx second delta x minus x second k of x second x prime. So since we have, we can notice here the property of delta distribution property here. And with respect to that, what is this expression? This expression, as I said, will be equal to k x x prime, because I am integrating over dx second of delta x minus x second kx second x prime. And at the end, what do I have? For a vector g, that is the integral operators on f is associated g of x is equal to integral a b dx prime omega x prime f. Let me first write k k x x prime f of x prime. Okay, so that means that G equal k f has its analytical counterpart that is g of x is equal integral ab dx prime omega x prime k x x prime f of x prime and that has the form of an integral representation for the function f of x, no, g of x, and justify the calling k x x prime the kernel of the operator k. So this is how I want to introduce integral operators, and more property is that the hermeticity of the integral operator depend on the property of the kernel k x x prime, and the integral operator is a continuous and Hermitian, but this I don't demonstrate here. Now I have probably a few minutes. I think I have 5 minutes. I continue, and now I introduce what I mean by formal differential operators. Formal differential operators. Okay. A linear differential operator L is an operator in a function space whose action on vectors f of this space is represented by a differential form x L f is a0x f of x plus a1x df dx plus a2 d square f of x dx square plus ANX dN, a space is missing, ANX dN fx dxn. So right here. A2x d2 fx dx2. Okay. So, and this can be written as x L f is LXF of x, where L of x is equal to A0x plus A1x d dx plus A2x d square dx square plus ANX dN dxn. Okay. The expression LX represent the differential operators L. Okay. So let me write that and let me check if I still have some minutes, so I should stop here. I think I should stop here. The symbolic expression LX represents the differential operators L defined in an abstract function space in the sense that Lx of f of x represents the vector L f. Okay. So, Professor Professioni, what do I do?
I don't know. I don't know. But I think if this is a good point to stop, Laure, I think we should stop here, because
Okay.
online lectures that take more than an hour.
Yes. Also, it is said an hour, and I think I use the 5 minutes I lost.
No. That absolutely
checking at the
fine,
beginning
but,
my files. Yes.
Plus minus an hour plus minus 10 is always okay. Yeah. Now
Okay.
I think this sounds like a good point to come in for today, and maybe we can still use a few minutes in case the participants have questions. I don't know if anyone has questions. Please just raise your hand.